Thank you very much for the opportunity to present at this conference. I've been learning a lot this week. So I guess with this talk today we have only theory talks, but I tried to be more motivated by experimental considerations. I'll report on a work I've done in collaboration with Subir Sajdev and Serhiy Krikhin, who is the true protagonist of this work and who fearlessly took all the technical and sometimes conceptual challenges that we encountered. So really, this work is motivated by the developments in, let's say, nonlinear transport in optics in the last maybe 10 or so years. In particular, the emergence of strong terahertz sources, which people nowadays are using to probe, let's say, collective modes, for example, of collective modes in superconductors. There are other techniques, the more familiar, like this pump probe. And one can use more advanced techniques using different pulses with different delays and frequencies to probe spin liquids and the broadening due to interaction in them. Then harmonic generation is sort of a familiar application that allows us to probe symmetry. For example, second harmonic generation implies inversion symmetry is broken in our material. And recently, I guess, using some nanopatterning and stuff like that, people also have used this in DC limit to probe the emergence of symmetry-broken phases in 2D materials. So what I want to talk about is the application of some kind of nonlinear transport probes to strange metals, and to kind of give you the motivation why we're doing this at all, apart from this is an available technique. So let me just give you a very simple overview of linear transport, and then I'll compare it with nonlinear transport and try to show you the difference. So the classical picture is that, okay, you have electrons, they're traveling through your solid, they're scattering, and when you probe the linear response, you get access to the following parameters of your electrons. You get their density, you get how often do they scatter, and you get their inertia. And in this kind of classical picture of transport, this is all there is, right? You almost completely defined the system. So the question arises, okay, does nonlinear transport give you anything of importance for metals, anything new, anything qualitatively new in particular? To understand that, we need to take more correct quantum approach to transport. So let's start with a semi-classical one with Boltzmann equation. And there, we know now that the electrons have a Fermi surface, and there is a dynamics of the electron distribution, which is, still starts with this sharp Fermi surface and the deformations thereof. The way linear transport works, you couple to electric field that creates a deformation of the Fermi surface that's this kind of dipolar-like in shape. And if you, convolute this with the velocity of electrons on this Fermi surface, you see there are more electrons here than there after the perturbation, so you get linear response to electric field. That's your Ohm's law. Now, if we go to higher orders and try to understand other like nonlinear contributions to current from electric field, it turns out that the story becomes a little bit more tricky. And here are two examples where things apparently go wrong. So first thing is that if you consider a Galilean invariant system, there is no scattering, and the velocity is proportional to momentum, then you can actually solve this equation exactly, no matter what the field is. What you get is that, a solution where the distribution function depends on this kind of shifted momentum. That's just solution of Newton equation of motion. And if you try to calculate the current, you just shift this integral in K and get something that's linear in E. And this is an exact answer to all orders in E. Therefore, there is no nonlinear response in this Galilean invariant system. Another illustrative example is that suppose you have a relaxation rate, you just do the usual tau approximation for the Boltzmann equation, and you linearize near the Fermi surface, so something we often do in class or something like that. And it turns out that then, again, the Boltzmann equation can be solved exactly, and if you try to compute the current, again, to all orders in E, again, you find that it's purely linear in E. So in both of these cases, nonlinear response vanishes exactly, which tells us that if we see nonlinear response, this means something non-trivial. In particular, there are two things that can lead to nonlinear response. Either, you break this relation, so your band in some sense is non-parabolic, or your scattering rate depends on momentum or on the energy of the quasi-particles. And this has been figured out quite a while ago. I think this paper illustrates it well. In the context of semiconductors, where near the bottom of the band you can consider nonlinear corrections, but also you can have a energy-dependent scattering from some Coulomb impurities with long-range potentials. So what does this all have to do with non-Fermi liquids? It's the scattering rate. So one way you can compare a Fermi liquid and a non-Fermi liquid is that the quasi-particle scattering rate in a Fermi liquid goes as energy of the quasi-particle squared, whereas in a non-Fermi liquid it will be linear. And here's a beautiful illustration of that. This ARPAS data on a high TC cuprate. So you can plot the momentum distribution curves. So it's basically just cut of this ARPAS intensity plot. And you can see that the higher binding energy you go, the broader the thing becomes, and this broadening linearly increases with binding energy. So that means that in a non-Fermi liquid, you have a much stronger, and even if you push it to zero temperature, low energy limit, non-analytic dependence of the scattering rate on energy. And perhaps because nonlinear transport is exactly sensitive to that, we could expect a strong nonlinear response. And basically in the rest of the talk, I'll try to convince you that exactly that's the case. The model of choice here is the Yukawa SYK model that Subir has talked about during this week already, and summarized most recently in this collection of papers. So here are its attractive properties. It gives you linear interior resistivity with Planckian scattering rate. It gives you the right frequency dependence of optical conductivity. It gives you T log T specific heat. So for phenomenological, let's say, purposes, it definitely sounds like a good theoretical model that you can study to study non-Fermi liquids and strange metals. So the technical challenge that we encountered, though, is that we have inversion symmetry. This is kind of a model with a symmetric circular Fermi surface. So if we want to study nonlinear response, the lowest nonlinear response is going to be there is third order in electric field. Doing diagrammatics for that sounds not like a good idea. So we wanted to derive the kinetic equation. And it has been done actually previously in these papers, for example, where here it was applied to the shot noise problem and recent experiments. But for nonlinear transport, what you realize is that there was an assumption made in these papers that the bosons, which are present in this model is of interacting fermions and bosons, and the bosons were assumed to be in equilibrium, right? So you drive the fermions, but the bosons are kind of just stay at the temperature. And if you do linear transport, that's kind of okay. So you go from equilibrium, you perturb it a little bit, the bosons don't couple to electric field, so that's okay, presumably. But if you go to nonlinear order, like already at order E squared, there will be some kind of coupling between fermions and bosons, and you would expect the bosonic distribution also to change. And when you go to E cube, and this is where we need to calculate, of course, these effects will start to matter. So what we need to do, which is a reasonable thing to do, is to derive a kinetic equation for coupled fermions and bosons in a quantum critical metal within Yukawa SYK. And this is basically the challenge that Serhii took on. So here's the model, just to guide you through this, what's happening step by step. We have electrons around the Fermi surface. There is some potential disorder, and there are these flavor indices, which are basically used to control the theory. You can say we're selecting a certain subclass of diagrams, or we're doing a saddle point approximation, which allows you to compute everything in the saddle point approximation. There's the critical boson with the mass that's at zero temperature is tuned to be at the critical point, to be at zero. And the secret sauce is that the coupling between the fermions and bosons is mediated by a coupling constant that's varying in space, and in particular fluctuating with zero average. We're not taking into account also the possibility of a constant coupling that's not varying in space, because in this particular model where all couplings are disordered, actually the equations become much more manageable. So we focus on this model, but this already model has a linear anti-resistivity, so it's, I think, good enough for phenomenological analysis of strange metal theory. Okay, so now the method of choice, how do we, yes? Okay.
Is the potential disorder important or no? You don't consider localization?
Well, no, it's a saddle point approximation, so there's not going to be localization. It just gives you some finite resistivity at zero temperature. I think that's more or less what it does, but it also helps with the Landau damping for the bosons. I mean, just you have a big scattering rate for fermions to begin with, and all these linear anti-corrections, they're kind of perturbative on top of that, if you wish. So that makes the calculation simpler in some.
It cuts off the temperature, at low temperatures it crosses over.
Oh, it doesn't cross over. It's just constant plus linear. And the constant allows you to treat the fermion-boson coupling like the boson self-energy becomes simpler if you have this constant scattering rate.
You keep it in the bottom of the
There's no localization effects here. So again, it's a saddle point. There's no. Okay. So then to derive kinetic equation, just to kind of so that we're all on the same page, we use Keldysh formulation of field theory, where we not only go from minus infinity to plus infinity in time, but to capture the nature, the non-ground state, non-equilibrium ground state, we kind of also have to propagate back. So we have this contour where, in principle, this is the same time for the top and bottom contour, but for the bottom contour, we always order it as it was later, as if it was later. And that allows you to, that implies that you have to introduce different types of correlators. The Green's functions that are not only time ordered, there are the retarded advanced ones, and this is how they look like, and this is, plus or minus for bosons and fermions. And because it's a commutator or anti-commutator, you can understand that, if you take these fields at the same point, same time, this is just one, so it doesn't have any information about the state. Yet these are fully renormalized quantum fields, so this Green's function can know about the interactions, they know about the spectrum of the system, but they don't contain the information about the occupation numbers, about the state. And that is taken care of by this lesser Green's function, where you take, one of the field on the top contour, one of the field on the bottom contour. So regardless of whatever times there are, they're always ordered in this fashion. And this average, of course, knows about the occupation number. So it's like, if you take average, it's like 1 minus the Fermi occupation number. Okay, so this is kind of lightning and fast overview of what's happening. Then what you do, you derive kind of Dyson equation for these correlators, for these Green's functions, and then you do a couple of simplifying steps. One is fairly standard. We want to work in a quasi-classical approximation. Basically, all our correlation functions depend on two coordinates, but then we go to Wigner transform, where we have the center of mass, which corresponds to essentially the fluctuations in real space, and the Fourier transform of the difference of the coordinates, and that corresponds to energy of the quasi-particles and stuff like that. And if your variations in real time and real space are slow enough, we consider homogeneous fields, and this implies a limit on how large frequencies we can consider in this approach. Then a lot of calculations simplify, and you can just get your functions to be functions of real space and momentum, similarly to Boltzmann equation. So the second step is more specific to this model. So the retarded boson self-energy coming from the interaction is actually here unrenormalized in non-equilibrium, which follows just from momentum conservation and the fact that you couple to the density of the fermions with this coupling. And the second simplification, again, arises from the spatially disordered type of the interaction, that the fermion self-energy is independent of momentum. So basically, the fermion, the momentum dependence of fermion's Green's function is the same as for bare fermions, which means that you can integrate over momentum and introduce these functions that are related to the lesser Green's function, but normalized by the essentially by the spectral function. And in case of fermions, it's just trivial, just gives you V Fermi or something. But in case of bosons, that gives you some function of frequency and momentum. As a sanity check, these equations all, of course, boil down to your familiar Fermi and Bose distribution and equilibrium. So that's a sanity check. And now I'm kind of proceeding to the next slide where I'm going to present actual equations. And okay, so the beauty is that once you introduce these two functions, it's all there is, right? There are two equations for two functions that you can reasonably interpret as occupation, as distribution functions for fermions and bosons, even if we are in a strongly interacting non-Fermi liquid. The thing being that they're all functions of this omega, which is the energy, the quasi-particle energy away from the Fermi surface for fermions, rather than momentum in the Boltzmann equation. Oops. Sorry, it was too much hand waving, I guess. And the structure is very similar to Boltzmann equation. So this term is in principle a little bit more complicated than just time derivative, but in many cases it's just this. Then you couple to electric field, and this is what is the momentum derivative in Boltzmann equation. Here it's just the quasi-particle energy derivative. And there are three types of scattering. There's disorder. There is scattering due to interactions of bosons being in equilibrium, and then there is a correction due to bosons being non-equilibrium, which you can say is like a fermion-boson drag. So to make progress with these equations, we also use angular harmonic expansion for all of these functions because we have a circularly symmetric problem. And then you realize two important things, that these drag effects actually only affect m equal to 0 harmonic. The reason being, again, that the interaction between fermions and bosons is momentum is completely spatially disordered. So it scrambles the momentum, leaves only the uniform component. And on the other hand, the disorder does not affect m equal to 0 harmonic because m equal to 0 harmonic is associated with energy, and disorder is just elastic scattering. So let's go, kind of order by order. So suppose we're talking about the left side being not at m equals to 0, and then the equation really simplifies to something very similar to a Boltzmann equation, where there is some renormalization of the time derivative and the scattering rate. So here's the disorder term, just your usual constant scattering rate, plus that's what comes from the interaction. And you can see the anomalous behavior of the scattering rate as a function of frequency. When frequency gets larger, temperature becomes small. It really becomes absolute value of omega. And the electric field enters like this. In particular, you take, the previous order in perturbation theory, you multiply it with electric field, and then electric field itself behaves as angular momentum 1 object. So in each higher order of perturbation theory, you either go up in angular momentum or down in angular momentum. And this is the way you proceed. So for example, if you do just linear response, you start from m equals to 0, and then you get plus or minus 1. And essentially, this is very similar to Boltzmann expression. There is the derivative of equilibrium distribution, and then there is a factor which takes into account frequency and the scattering rate, including this anomalous component that would be of interest to us. So then you can continue doing this process. So you go from the first order to second order, and then there are two options. You can either produce m equals to plus or minus 2 angular momentum, plus or minus 2 harmonic. So it will be some kind of quadrupolar distortion of the Fermi surface, or you can produce a symmetric distortion of the Fermi surface. And so this is m equals to 0, and this is a special case, so I'll return to it in the next slide. Then when you go, and obviously these are both even harmonics, so if you try to calculate their contribution to current, which is odd harmonic, you're going to get 0, but in third order, you can go back from 0 and plus minus 2 to plus minus 1 and get a contribution to current. So that's where what we're going for, but before that, I need to discuss this case. Okay, what's happening here? It's different. And this is precisely why all this kind of thing has to be developed, because you see that there is a coupling between the bosonic distribution and fermionic distribution. And you have to solve that somehow self-consistently. The answer looks like as if you just put in some other scattering rate, but there are two important, let's say, one sanity check, one result. So the sanity check is that if you take these two equations as given and solve them, then the scattering rate for this zero angular momentum harmonic becomes actually zero. The reason being is that this harmonic corresponds to pumping energy into electrons. And if we have a system that is closed, there are bosons and fermions, but nothing extrinsic, we're pumping energy into it, it cannot relax. So the relaxation rate has to go to zero, and it does, which is a good sanity check that we have energy conservation, which is in the Hamiltonian. Now, if we force the bosons to be in equilibrium, suppose for some reason these bosons, I don't know, scatter much stronger off lattice or something like that, then you can go through these equations, and you can also get this result, which corresponds to a scattering rate, and that's going to be linear in T. Now, this is not an approximation that's motivated by anything. Well, maybe slight motivation comes from the fact that if you assume kind of equilibrium distributed bosons, you do get nice results for the shot noise, which was shown by Subir and Alex Nikolaenko. So it might be phenomenologically motivated for them, but I think it would be interesting to consider coupling, to real lattice or some external bath. Okay, but the most important corollary of that is that the scattering rate for this harmonic, for the m equal to 0 harmonic, is much lower than for all the other harmonics. For all the other harmonics, you just get this dominant contribution of disorder. Here you have to have inelastic processes coming into play. Okay, so then if you proceed to the final answer, so this is also reflected in what you get in the current or nonlinear conductivity. So essentially the heating, the response due to heating of the system is dominant because the scattering rate is much lower due to inelastic scattering. But there is also a contribution here that comes from creating this quadrupolar distortions of the Fermi surface. And something we're working on right now is that in principle, if you, I didn't put frequency here, but if you do, you can measure the scattering rates corresponding to this quadrupolar distortions of the Fermi surface. This is not the most optimal model for that because it's circularly symmetric. So, and all scattering rates in all channels are the same. But if you introduce the lattice, you'll actually have two different quadrupolar distortions, and they are of interest with respect to pseudogap physics and even anisotropies in a non-Fermi liquid state. So I can talk about this more if asked. But what I want to really focus on is that there is a prefactor here in both of these expressions, and now I'm going to try to estimate that or give you some expression and argue what happens. So if you go to the third order response, so the structure of the expression, you can see you're taking these derivatives of the distribution function, but with the scattering rate. And if you do these derivatives and follow through, what happens in the third order current is that you get second derivatives of the scattering rate, which was non-analytic. And because of that, so for example, if you naively, so these are the derivatives in frequency, in energy. So if you take zero temperature limit, this is absolute value of omega. So if you take second derivative, you're going to get a delta function. But if you do this at finite temperature, instead of a delta function, you're going to get 1 over t result. Okay, so there's some prefactors, but what matters is that it goes as 1 over t. So what I've just kind of demonstrated to you is that you have a non-Fermi liquid, and if you calculate the third order response, third order optical conductivity, it actually blows up as 1 over t in temperature, so it becomes massive. And for a Fermi liquid, in contrast, the scattering rate just goes as energy squared, so its second derivative is just a constant. So there's a dramatic difference in low temperatures between nonlinear responses of a non-Fermi liquid and a Fermi liquid, with non-Fermi liquid having much stronger nonlinear response. So this is an interesting result of a obviously quite complicated calculation. So can we get that in 3 lines? So let's try. So here's our conductivity. and you know, we know that in this model, the resistance has a linear in T correction. We know that in second order, we're pumping energy in the system, so there's some kind of heating, and we can estimate the change in temperature just by balancing, you know, the Joule heating power. There is a scattering rate that gives us energy, and yeah, we have the energy stored in the system, which is specific heat times the temperature change. And that gives us a correction to sigma that is of order I squared, so that corresponds to third order conductivity, and that, according to this formula, is just the inverse of specific heat, which gives you 1/T in this case. Yeah, if I would have done that in a, so in that case, this 1/T is kind of exactly reproduced, but the origin of this really is this strongly frequency and temperature dependent scattering rate, and not the fact that C is linear in T. So this gives you the right estimate, but the real origin is this very strong scattering and its energy dependence on a non-Fermi liquid. Okay, so yes?
Suppose that scattering rate scales in between the Fermi liquid and non-Fermi liquid with some exponent which is less than 2 and larger than 1. What will happen to this 1/T singularity in this case? Does it show up immediately and you go below 2, or you go all the way to 1?
I think you probably will get a power law, right? So as long as, okay, as long as I differentiate it 2 times and I get something that blows up, so just mod omega gives you delta function. If you take some omega to alpha, you will get omega alpha minus 2. So as long as that diverges, yeah, I think you should get some power law. Yes. If it's just log, if it's omega squared log, then you differentiate it. Okay, you'll get log correction. Yeah. Okay, yeah. Valid point. Yeah, I'm actually almost done. So I want to kind of okay. So I want to speculate a bit, because if there's something that's blowing up, so we also ask this question. Okay, I mean, it doesn't make sense. So that means that probably something is going wrong, but I think the answer to that is, as often the case, if you see a divergent term in perturbation theories, you have to sum the perturbation theories. And Sergey has done that estimate for what happens in higher orders in perturbation theory, and they indeed blow up even faster and faster and faster, but the only thing that means that potentially, if you resum this whole thing, you can see that there is some ratio that enters like in each order, that you will get a scaling behavior for the nonlinear contribution to conductivity that will be essentially scaling as a function of electric field over temperature and those scattering rates. So that's kind of the conjecture. We didn't solve the full nonlinear equation, but that's more likely, I would say, way out of this diverging expression blowing up. So let me now round up what I told you. So here's kind of what we add to this nice phase diagram you've seen many times. So what we knew before is that we have resistivity that goes as T squared in a Fermi liquid. There is a prefactor here that when you go to some, let's say, quantum critical point, it's going to blow up. But in reality, it's not going to blow up to infinity. Instead, this coefficient becomes 1/T, which leads to linear T resistivity. A very similar thing happens to nonlinear conductivity, but nonlinear conductivity in the Fermi liquid goes as constant at low temperature, which means that the same factor gives you 1/T in a strange method. So with that, I'd just like to conclude. So what I've demonstrated to you today is that nonlinear transport in non-Fermi liquids can be interesting because there is a reason for it to be strong, because the scattering rate is strongly energy dependent. We conjecture a possible even scaling regime in nonlinear transport close to quantum critical point. And a work in progress that I think is also interesting for probing strange metals and non-Fermi liquids is that with nonlinear transport, you can measure, excite, and measure the relaxation in different angular momentum channels on the Fermi surface. at essentially a low frequency and electronic low frequency scales. Thank you for your attention.
I just wanted to probably follow up on Leo's question about potential disorder. So did you say or at some point that I should look at this, let's say, T term in the resistivity in your model as a correction to the residual resistivity, or it can live on its own and it doesn't need any help from disorder?
So the fact is that if you calculate resistivity, then if you take the interaction to be like strong, then the slope of that linear anti-resistivity does not depend on disorder. I think that's the statement.
Right. So, but then you can just take it away, right?
Yeah, of course. Yeah, you could.
Which means that you have umklaps, right?
I mean, you don't have momentum conservation here anyway because your interaction is disordered. It's fine. It's just you can think of it on the one hand from phenomenological perspective. There's always a finite slope. From more calculational perspective, it just makes calculations simpler when you have this big imaginary part and the integrals become simple. That's all.
Okay, just a regularization.
It's not a linear transport. You can certainly remove the
yeah, you can.
Scattering, and then you still get the linear.
And nothing changes.
It's harder to work with.
Yeah.
So for linear response, we have a universal understanding about the Joule peak. For example, the Joule weight is basically given by overlap between current operator and the momentum operator. And the Joule peak is coming from the transitional symmetry. So is there any universal understanding for this kind of like nonlinear response formula, like where the overlap between the current and the momentum may comes in, and also like it seems like there are 4 like Joule peaks. If I
you want to relate it to some conserved quantities? Is that
yes,
the essence of
yeah.
the? I mean, the thing is, even like a Fermi liquid that's clean, none of these guys. I mean, this guy is not a conserved quantity, right? So there will be, yeah. I don't think there's a way. Like, okay, momentum is conserved because translational invariance, right? Energy must be conserved, you know, because we have a closed system. But the quadruples should not be conserved at all. So we didn't really think in that direction.
But I thought like in the cubic level, you have only the you only have the momentum channel, right?
But look, to get there, you have to go through this guy, right? So actually this response is mediated by the quadruple that's not a conserved quantity. So yeah, I'm not sure there will be such universalities for nonlinear responses.
Thanks.
I know what you mean, but this is a theory that doesn't have translation variance, at least on sample to sample, so there is no distant momentum. That whole thinking doesn't apply here at all.
Yeah, but even in a clean system, this quadruple will not be a conserved thing. So momentum will be conserved, but yeah.
Okay. Yeah, sure, thanks.
I'm curious how the results generalize. Say if you only assume some kind of reactor volume driving the translation, you don't assume specific orbit. You say the electron wave function is independent momentum, making assumptions. Do most of the derivations still go through? I'm guessing you plug in the scattering rate at that last step, or is it that there's some important details of how SYK that enters the calculation?
So I think the Yukawa SYK details probably come in so okay, these two things, it's not even like if you add the non-disordered interaction, I think it's gonna become much more complicated because these things are explicitly arising because, you know, there is no momentum conservation in any vertex. So essentially you're integrating over each momentum separately, and that's why you get all these nice results. So
once you make that assumption, then your final formula will just be dependent on two scattering grids, which can be model dependent. It doesn't really mean the specific how SYK.
Yeah, no, I agree. So it's similar to kind of Range-Kadanoff kind of things, and you know, with in principle it's probably is, but again, for a non-Fermi liquid, I think there would be, at least for linear conductivity even, right? So this model, if you don't take everything is disordered, a lot of diagrams just kind of like vertex corrections cancel. Now, if they don't, this probably will become much more complicated.
Yeah, I had this question about this interpretation that you gave in terms of the specific heat and how much the sample heats up. Specific heat is T log T, so how does the log disappear?
Yeah, I've been asking myself this question, but also as far as I understand it, and probably you're the person to answer that in this model specifically, well, I mean, so the specific heat goes as, so there is the just linear NT part, and then there's this other part, and we didn't like compute it ourselves, but we didn't find any statement whether it's log or something like log. It kind of grows, but I'm not sure if it's log or not. So, well, one thing.
It's not exactly a log.
Sorry?
It's not exactly a log.
Yeah, so I guess that's one thing. Yeah.
Yeah, the specific heat should have a log asymptotic.
I think it does, definitely. It has been checked for the model with uniform interaction too. There, I think it was checked that it's T log T. For this model, so there's kind of, yeah, one has to figure that out a bit. But, so I agree. So in that estimate, this log T doesn't, I mean, you can put it there, but, yeah. From let's say order of magnitude estimate, it wouldn't change much, and whether this estimate should be taken more seriously than just a heuristic, that we can discuss. Not 100% sure, because you know the real origin is this scattering rate being dependent on energy.
Yes, I'm sorry for the naive question, but like I'm trying to understand. Once you have this Yukawa coupling, so its density, it's part of the whole channel. So its density coupled to 5.
Sort of, yes. Well, modular the indices and that stuff, right? But it's in the density.
So I'm wondering whether, you know, on the coarse grain you now generate a linear phi term, and what do you do with that? So you kind of explicitly seems like that will explain a bit
Yeah.
the symmetry of the bosonic thing.
No, actually.
Like a random field like that.
Well, no. So if you want to generate a linear term, you're gonna average of this guy linearly too, right?
I'm not gonna average of it, but I coarse grade for arbitrary, for particular configuration of G's.
Okay, but then I mean, in reality, what you need to do, right? You have to go. You have to average over this thing first, right? And what's going to happen once you do that? You're going to have like an interaction that's going to contain 2 of these guys and 4 of these guys.
No, I'm not going to average over.
So if you're not going to average, then
I'm going to generate, like, take the V term and the G term, so now think of this.
Just asking whether we can take a ring field.
I'm only going to average over. I'm only going to coarse grade over the fermions with the V term. So now I have like an effective random field that's a product of G prime and V. So
yeah, no, I understand what you say. I think this goes back probably to Subir's talk where they studied actually like the problem with this disorder on the bosons. I think in large N approximation, the saddle point corresponds to actually that effect being washed out in some sense, because you do average over both indices and space. So it's like Born approximation, right? You don't really think too much about, like, on average, the system is translationally invariant. But the
average V is 0.
Exactly, average V is 0, average G is 0, so they just go out of the picture.
Yeah, so there may be something for everything. I'm not sure.
I think those effects that you talk about, like, they will come into play once you go beyond the saddle point, right? Then you start studying correlations between fluctuations here and there, of course.